This lesson encompasses topics 4 and 5 in your textbook, bringing together the ideas of the periodic table. So remember, elements are made out of only one kind of atom, and all atoms of the element are identical. Elements are identified on your periodic table by a symbol. These symbols always include one capital letter, and they may also be followed by a lowercase letter. This is kind of optional. Not every element has 2 letters in their symbol. For instance, we see that carbon is just a capital C. Remember, the first one always has to be a capital letter. Sulfur is just a capital S, 1 capital letter. Whereas cesium has both a capital and a lowercase letter. Okay, so this is still representing one atom because there is a capital and then a lowercase. Be very careful how you're writing this because capital C, capital S is a compound where capital C, little s is an element. And this is a very big deal. Okay, so making sure that it's clear what is a capital and what is not when you are writing elements symbols. Every element on the periodic table has an atomic mass or an atomic molar mass, also known as just a molar mass. Elements in the periodic table are listed in order of their atomic mass. If you followed along with element number 1, 2, 3, 4, 5, 6, whatever, continuing on, you would see that their atomic mass is increasing each time. Atomic mass is the mass of one single atom of an element. It is represented in atomic mass units, or AMU. 1 AMU is equal to 1.66 times 10 to the negative 1.6605 times 10 to the negative 27 kilograms. That would be a decimal where it's 26 zeros, 26 of those, and then 16605 kilograms. So very, very small number. Most are commonly represented with units of grams per mole. So for instance, the atomic mass of hydrogen is 1.01. So we could say that's 1.101 AMU, but most often in chemistry, we will say that is grams per mole. You don't need to understand that unit yet. It just is the unit of atomic or molar mass. Both protons and neutrons contribute to the atomic mass. So within an element, or an atom, all of the mass is really coming from protons and neutrons. The mass of an electron is negligible. All right, negligible means very little or not a large contributor. Just as we were talking about, atoms are composed of protons, neutrons, and electrons. Protons are positively charged. Okay, they are located in the nucleus, looking at kind of a Bohr diagram here. Neutrons have a neutral charge, aka they do not have a charge or a charge of 0. They are also located in the nucleus. Electrons are negatively charged, and they are located in clouds around the nucleus, or in Bohr's model, orbiting like the sun and Earth. So I have posted a periodic table within our chemistry folder. So go to the chemistry unit homepage and look through the Google folder. I think it's at the very bottom, unfortunately, and it's the periodic table that we would use for Science 10. Okay. One thing to note, we do not need to use this number here. Okay, so the second number is unimportant to us, so we won't look at that one. So reading the elemental information, the atomic number is in the top left here. Okay, so we are looking at the element titanium. The atomic number for titanium is 22. It represents the number of protons in the nucleus of one atom. A proton is typically denoted by a P with a plus as a superscript. So it's the number of protons for that atom. If you change the number of protons, you change the type of element you have. So 23 protons is no longer titanium. It is the next element on our periodic table. It also represents the number of electrons in the element. We have equal number of positive and negative charges in an element. So if I have 22 protons, titanium will have 22 electrons as an element. Because we have 22 positives and 22 negatives, overall that is a zero charge and it is a neutral element. Also listed on our periodic table is the common charges. So sometimes it's just one charge. Other times elements can have multiple common charges. The most common charge is always listed first. So the most common charge for a titanium ion, different than a titanium element, is 4 because it's listed first vertically. We can also write these horizontal in periodic tables, but again, that first charge is the most common regardless of whether it's written horizontal or vertically. So when the element becomes an ion by losing some of these electrons, it will always lose electrons to become this charge, whether it is 1 or 2 options. So this tells me that titanium as an ion typically likes to have a 4+ charge. To have a 4+ charge, it needs to lose 4 electrons. So titanium most often will lose 4 electrons when it becomes an ion. Ions are formed when we create a compound. This is a little bit beyond grade 9. Okay, just recognizing what we're seeing on our periodic table is the most important thing here. All right, the elements symbol, of course, is our 1 or 2 letters where the first letter is always a capital, and if there is a second letter, it is always a lowercase. The element's name, of course, is titanium here. Now, in our diagram, we also have the atomic or molar mass, and that is this number here. The atomic or molar mass always has 2 decimals, or for the most part always has 2 decimals. Again, it is the mass of only one atom in units of AMU or grams per mole, where grams per mole are the most common. The atomic molar mass represents the number of protons and the number of neutrons. Remember, that's what makes up its mass. Now, let's calculate the number of neutrons for titanium. So titanium, we know, has 22 protons. That is its atomic number. So plus the number of neutrons, which we don't know, will equal 47.87. So I will, to get N by itself, I need to subtract 22 from each side. So I get that N is equal to, and this is again the number of neutrons, is equal to 47.87 take away 22. That gives us 25.87 neutrons. Now neutrons do not come in decimals, so we will always round up or down. So because our decimal, this value here is greater than a 5, or 5 or greater, we're going to round up. So we would say that titanium has 26 neutrons. So again, the number of protons plus the number of neutrons is equal to the atomic molar mass. If I rearrange this, neutrons, the number of neutrons is equal to that atomic mass minus the atomic number or the number of protons. This is something you need to know. In our periodic table, the state at room temperature can also be inferred from our periodic table. So it is based on the background color. sorry, not the background color, the color of the element's symbol. So because titanium is written in black, we know that titanium is a solid at room temperature. If titanium's symbol was red, it would be a gas. And if it was blue, it would be a liquid, which we write with kind of like a cursive L, so that it doesn't look like a 1. So determine the following for nickel and bromine. So let's look at just nickel first. So nickel's symbol is Ni. If you find it on our periodic table, it'll be in our transition metals. Its atomic number is 28. The molar mass is 58.69, and I'm going to use units of grams per mole because that's what I'm most familiar with. The number of protons is always equal to the atomic number. So nickel has 28 protons. The number of electrons is always equal to the number of protons. So nickel also has 28 electrons. If I want to calculate the number of neutrons, remember that would be our atomic mass, so 58.69, take away the number of protons, so 28. We're left with 30.69, which we need to round to a whole number. Therefore, I would round up to 31 neutrons. The most common charges for nickel are nickel 2+ and nickel 3+. The state of nickel at room temperature is a solid because nickel, its elemental symbol, is black on our periodic table. Bromine, on the other hand, it has a symbol of Br. Bromine's atomic number is 35. Its atomic mass is 79.90 grams per mole. The number of protons in bromine is 35, always equal to the atomic number. The number of electrons is equal to the number of protons. Therefore, there are 35 electrons. To calculate the number of neutrons present, we will take our atomic mass and we are going to subtract the number of protons. When we do this, we get 44.90. We need to round that up to 45. The most common charge for bromine, the only charge for bromine, is negative, so -1. The state of bromine, because bromine is blue on our periodic table, it is a liquid at room temperature. So it's important if you're going to print your periodic table that you print it in color if at all possible, because the colors are important. Let's talk about that periodic table. Mendeleev organized the known elements at the time in 1869, there were only 63 elements that they'd figured out at that point, based on atomic mass. He wrote all of these elements that they had discovered on an individual card, like a little sticky note, and he wrote the atomic masses. So the first thing he did was he organized them by atomic mass in increasing order. And then he started to put elements with similar physical properties and similar chemical properties into families. That's what he called them. These were groupings, and he could see that he could still keep them in order of molar mass or atomic mass and group them with respect to their physical properties. So he started to compose what we actually know the periodic table to be today. He left gaps in the table for elements that had not yet been discovered. He was able to predict, based on his previous idea of families, the physical and chemical properties of the atoms that would fill these gaps. He is still correct to this day in all of those predictions that he'd made. So, again, Mendeleev put these in order in terms of atomic mass. Then he grouped them based on properties. So instead of having one long list of all of our elements, we have stacked some of them on top of one another. Where they are stacked, these were his families and what we currently call groups. Okay, so a column of elements will have similar chemical and physical properties. Elements can also be classified into metals, metalloids, or nonmetals. There's a stairway that divides metals and nonmetals. To the left and underneath this stairway, which is here, are metals. To the right and above the staircase are nonmetals. Along the staircase here are what we call the metalloids. So, some properties of metals. Metals, except for mercury, at room temperature are solids. All right, all of our metals are solid except for mercury. Now you might see that some of them are hollow on our periodic table. It just means that their state at room temperature is unknown because they don't exist at room temperature. Some elements are man-made and are unstable at room temperature and pressure conditions. So they break down. So they've never actually seen these elements at room temperature, so they don't actually know what their state is. That is what a hollow kind of symbol looks like or means on our periodic table, for those of you who may ask. All metals are good conductors of heat and electricity. Some are better than others, but in general, they will all conduct. They are lustrous, which means they are shiny. They are malleable, which means they can be shaped without breaking. So if you hit a metal, it's not going to shatter into a bunch of pieces. It will bend. Metals are ductile, which means they can be stretched into wire. And metals are found again to the left of the staircase. There's one exception, and that is hydrogen. Hydrogen is not a metal, even though it is on the left-hand side of the staircase. Hydrogen belongs with the nonmetals, so don't confuse it. Nonmetals can be a solid, a liquid, or a gas. If you look at all of their states, all of the colors of their elemental symbols, they have all three within that side of the periodic table. All nonmetals are poor conductors of heat and electricity. They are dull, not shiny when they are solid. They are brittle, which means they break. They do not bend under pressure. So again, if you hit them with a hammer, they would break or shatter. They would not bend. They cannot be made into wire or thin sheets. Again, they are found to the right of the staircase with the exception of hydrogen. Hydrogen is on the other side, but it is still important to consider as a nonmetal. We've seen some examples here. You can see carbon is a solid, phosphorus is a solid, sulfur is a solid, and they are totally different. They are not shiny. Carbon kind of looks shiny here, but carbon can be a diamond, which isn't necessarily shiny or lustrous. Carbon can be graphite. Carbon can be soot. So we're looking at one type of carbon here. We can see that they are all different states. Chlorine is a gas at room temperature. Bromine is a liquid. And iodine is a solid. The metalloids have properties of metals and nonmetals. So they can be shiny or dull. They can be brittle, but not ductile. They may or may not conduct electricity. Like silicon is a great conductor. Boron is not. They are found sitting on and around that staircase. Some examples are boron, silicon, arsenic. So you can see that arsenic is dull, whereas germanium is very shiny. So we can have some very different properties within our metalloids, and they are not as predictable. So in our periodic table, there's a couple other things. We also start to talk about the transition metals. And the transition metals are these guys in the middle here. Okay. These are our transition metals. They're a little bit different than our regular metals. They conduct electricity. They're shiny. But in comparison, they have higher melting points, density, strength, and hardness than other metals. These are just typical properties. Some don't do that, okay? Some of them break the mold, like mercury. Mercury is a liquid. So the fact that it doesn't have the higher melting point than everything else is kind of an anomaly, or sticks out from the crowd. The other part of our periodic table is the lanthanide and actinides. Okay, so we get these guys at the bottom, and these are all radioactive, and most of them are man-made in lab settings. So they're either made under really high temperatures and pressure conditions, or really low. They're made in like particle accelerators, so they're kind of unstable. They decompose into other elements, or they just simply fall apart when these temperature or pressure or vacuum conditions are changed. So these are some extras in our periodic table. Just in case I use these words, mostly the transition metals, we don't really talk about these guys too often, but just generally the transition metals are these blocks this block in between our periodic table sides. The periodic table, again, I had kind of mentioned this, is organized into groups. So atomic mass is increasing as we work through all of the elements in order. Then what they did is Mendeleev organized them by their properties. So groups are these columns, and periods are rows. Now we can have a full row like this. Our first row just contains 2 elements. Our next row contains 8, and this row contains 18. So we can have various different numbers of elements in each of these. We also have groups here, don't forget. So just some shorter groups. Again, they are based on their properties. You will need to know the properties, which we're going to talk about very shortly here, of group 1, group 2, group 17, and group 18. Transition metals, again, get a little hairy. They're a little bit different. They can have lots of variety, so we really don't include them in what we're going to talk about. But these 2 on each end have some very predictable properties. So groups 1 and 2. Group 1, that first column, is called the alkali metals. These are typically very soft as a metal. They can be cut typically with just like a plastic knife. They don't occur freely in nature because they are super reactive. So in nature, they are combined in compounds. They're not just found in a pure form. They're very reactive because they have an unpaired electron. They easily give up an electron to form a compound, and that's why they are all found in compounds. They need very special storage because they react when they are exposed to air or water. So a piece of metal from a group 1 alkali metal is actually kept in oil because oil repels water and it will completely seal around that piece of metal. Examples are lithium, sodium, potassium. Group 2 are called alkaline earth metals. Again, they are not freely found in nature because they are very reactive. They are found in compounds and we have to purify them. They don't react quite as strongly as an alkali metal. So alkaline earth metals have a little bit less of a reaction with air and water. Examples are beryllium, magnesium, calcium, etc. If you are curious about how reactive these metals are, take a look at this video. I will link it in our notes below, and see what happens when we put a piece of rubidium in water. Group 17 and 18, the opposite end of our periodic table. Group 17 we call the halogens. These are non-metal elements. They are the most reactive nonmetals. Okay, so they are not nearly as reactive as our metals, the alkali or alkaline earth, but they are reactive in comparison to all the other nonmetals. It's because, again, they have that unpaired electron. Examples are fluorine, chlorine, bromine, and iodine. Group 18, the last group of our periodic table, are called the noble gases. They have the maximum number of electrons possible in their outer shell, and this makes them super stable. They're content. Electrons either want to be in a full shell or an empty shell, okay? Or elements want a full shell or an empty shell of electrons. And so because the noble gas has a full shell, they're chill. They don't want to do anything else. They don't react with anything else. They are typically found on their own and not in compounds for that reason. They don't react. Examples are helium, neon, krypton, etc. For practice, take a look at the learning guide for this topic.